Racing through the cosmic void, a blazing visitor from another galaxy. NASA says the comet is now closing in for its closest pass by our planet. And the world's telescopes are, of course, chasing it frame by frame before it vanishes forever.
If you've been watching our channel, you know we've been following 3I Atlas for months now. Recently, NASA released a new Hubble image of 3I Atlas. At first look, the image seems simple. It shows a tiny point of light surrounded by a smooth blue glow. It almost looks boring. An independent astrophotographer who has been tracking this object night after night says that image does not tell the full story. What Hubble saw, and what the raw data still shows today, looks very different. This video is made possible by Ray's astrophotography. The observations you're about to see come from his careful tracking of 3I Atlas over time. Please check out his channel and support his work. The link is in the description. What Ray noticed in the new Hubble image. When Ray first saw the newly released Hubble image of 3I Atlas, his reaction wasn't excitement or amazement, but confusion. The image showed the object as a very small, sharp point of light, sitting inside a much larger blue coma, clean and compact in a way that immediately felt off to him. At a quick glance, it almost looked like a distant star with a soft glow around it, rather than an active comet-like object. And Ray didn't arrive at that reaction casually. He's been imaging 3I Atlas from the ground again and again, watching how it behaves over time, so when something suddenly looks very different, it stands out. One thing Ray was quick to clarify is what he was not worried about. A lot of people online immediately focused on the hexagonal shapes visible in the Hubble image and started speculating wildly about them. Ray addressed that directly and said those shapes are most likely optical artifacts, caused by the way light passes through Hubble's mirror and support structure. In simple terms, they're quirks of the telescope, not features of the object itself. But that wasn't the issue keeping him up at night. The real problem was much simpler and much harder to ignore. The object itself looked wrong. Ray had never seen 3I Atlas appear as a clean point of light before. Not in his own images, not in earlier Hubble images, not in any data he had worked with. So the obvious question forms almost instantly. How did Hubble suddenly capture 3I Atlas as a point source when it never looked that way before? If an object has always looked extended and structured, and then one day it suddenly looks like a dot, wouldn't you want to know why? Of course you would. And Ray did too. He pointed out that in previous images, including older Hubble observations, 3I Atlas appeared much larger and brighter, with visible structure and a clear sense of direction. There was a head, and there was material trailing behind it. It looked active and spread out, not compact. So when the new image showed a tight point of light instead, Ray couldn't brush it off. Another important detail here is that Ray wasn't comparing one picture to another in a casual way. He has a running visual memory of this object because he's been tracking it repeatedly. When you observe something night after night, you don't just remember one frame, you remember how it behaves. You remember its shape, its brightness, and how it changes. That's why this stood out to him immediately. It was a clear change in how the object appeared. So Ray asked himself a very grounded question. Is this something new about the object, or is it something about how the image was made? Instead of guessing, Ray chose the most straightforward option available to him. He decided to take a closer look at the released image itself. He zoomed into the JPEG that NASA published and studied it carefully. What he saw only deepened his confusion. The core of the object stayed tight and point-like, even when zoomed in, and much of the surrounding structure he was used to seeing just wasn't there. It wasn't that the image was low quality, it was high quality, polished and clean. But that cleanliness was part of the problem. So rather than speculating about motives or jumping to dramatic explanations, Ray decided to check whether the published image actually reflected what Hubble recorded. He navigated to the Hubble archive, located the specific observation from December 4th, and downloaded the raw files. NASA makes Hubble's observations publicly available through an official archive, which means anyone with the right knowledge and patience can download the original files. And this is where Ray's curiosity turned into something more serious, because the moment he opened the raw data, even without processing, even without color, the object appeared larger and more extended than what the published image suggested. That alone told him that something important was happening between the raw data stage and the final released image. Because if the raw data shows something larger and more complex, why does the image shown to the world look so simple? What the raw Hubble data shows. Once Ray decided to stop guessing and actually check what Hubble recorded, the very first thing he did was download the raw images taken on December 4th. These are the plain black and white files that come straight from Hubble's sensors, before any heavy cleanup, color choices, or smoothing is applied. In simple terms, this is the closest version of the data you can get to what the telescope actually saw at that moment in space. When he looks at the details of those files, one thing jumps out immediately: the exposure time. Each image was taken with an exposure of about 270 seconds, which is roughly 4.5 minutes. For an object as bright as 3I Atlas, that's a very long exposure. Let me ask you something simple. Have you ever taken a photo of a bright lamp at night and ended up with a big white blob instead of a clear shape? That's what happens when too much light hits the camera. Ray explains that the same thing happens with telescopes. When you expose for too long, bright objects lose detail, edges blur together, and structure turns into smooth glow. We're talking about a basic trade-off here. Long exposures are great for faint objects, but for bright ones, they can actually hide information. Ray points out that earlier images of 3I Atlas used much shorter exposures, sometimes around 40 seconds, and those images showed far more structure and motion. So when he sees 4.5-minute exposures used on a bright, active object, he immediately starts wondering why. Alright, so what does he actually see when he opens the raw files? Well, 3I Atlas does not look like a point of light. Even without any processing, even without color, the object already looks larger and extended. There's a broader core with surrounding material, and it doesn't just collapse into a tiny dot. And this is important because it tells Ray that the compact point seen in the released image is not coming directly from the raw data. Now, Ray doesn't stop there. He starts processing the images himself, step by step. He applies cleanup steps to reduce noise, similar to what NASA does when preparing images for release, essentially trying to see if, by following reasonable steps, he can honestly recreate the image that was shown to the public. And here's where things get interesting again. Even after processing the raw data carefully, Ray still ends up with images that show more structure than the released version. The coma stays larger. The object does not fully shrink into a clean point. The extended features don't disappear the way they do in the public image. So this tells him that the difference isn't just about raw versus processed. It's about how far the processing is pushed and what assumptions guide it. At this point, Ray introduces a concept called Point Spread Function Modeling, or PSF for short. Now, don't let the name scare you, because the idea is actually simple. No telescope produces perfect points of light. Light spreads slightly as it passes through mirrors and lenses. PSF modeling is a math-based way to understand that spreading and correct for it, so images look sharper and cleaner. It's a normal tool used all the time in astronomy. But this is the key detail Ray focuses on. PSF modeling assumes that the object you're looking at behaves like a point source, meaning most of its light comes from one small central spot. That assumption works great for stars, but Ray asks a very fair question. What if 3I Atlas is not acting like a simple point source? If the object is actually extended, with real structure and uneven brightness, Then applying strong point-based sharpening can flatten those features. The software doesn't know what's real and what's not. It only follows the rules it's given. And if the rule says, find the point and sharpen it, the output will move in that direction. So let me put this another way. If you tell the software to look for a dot, should we be surprised when it gives you one? Probably not. And this is why Ray believes PSF modeling likely played a big role in turning an extended object into the compact point seen in the released image. Ray is careful about how he explains this. He doesn't say PSF modeling is fake or dishonest. Instead, it's powerful. And because it's powerful, it needs to be used carefully. Processing choices, far from being neutral, have a key role in shaping what survives and what disappears. When you combine very long exposures with point-based sharpening, the result naturally favors smoothness over complexity. So if two people start with the same raw data and end up with images that look very different, what caused that difference? It was the choices made during processing. Ray even explains that when he tries to push his own processing further to match the released image exactly, he has to suppress structure that is clearly present in the data. In other words, to get that clean point, he has to remove information. And without a clear scientific reason to do that, he's not comfortable going that far. This is where Ray's concern becomes very clear. The raw Hubble data shows 3I Atlas as an extended, bright object. His own processing confirms that. His backyard images support it. And yet the image released to the public presents something much simpler. That doesn't automatically mean anyone is wrong, but it does mean something important is being filtered out. What Ray consistently sees in his own observations. Now this is the part Ray keeps coming back to, because it's the part he trusts the most, his own repeated observations. Night after night, from his backyard, using the same equipment and the same careful approach, 3I Atlas keeps showing him the same overall shape. It doesn't matter if the sky conditions change slightly or if he tweaks his processing settings. The object consistently appears with a cone-shaped front, followed by an elongated structure trailing behind it, almost like the object has a clear direction and flow rather than being evenly spread out in all directions. So, if an object keeps showing the same structure across many nights, many images, and many processing attempts, does that sound like an accident? Probably not. And that's exactly why Ray pays so much attention to repeatability. In astronomy, seeing the same thing again and again is one of the strongest signs that what you're seeing is real. Beyond the basic shape, Ray also keeps noticing something even more interesting in the trailing region behind the cone-shaped front. He sees spherical or tornado-like jets forming and moving over time. These are not straight, simple streams, but rather they appear to rotate or spiral, almost like material is being pushed out while spinning. And this isn't based on a single still image. Ray sees this motion clearly when he creates time-lapse sequences from his data. This is where his choice of exposure time becomes very important. Ray usually works with shorter exposures, typically in the range of 40 to 60 seconds. These shorter exposures don't collect as much total light, but they preserve detail. They freeze motion instead of smearing it out. And when Ray lines these frames up over time, he can actually watch the jets move, swirl, and shift position. Now, if you want to see motion, would you use one very long exposure or many shorter ones taken over time? The answer is obvious. Motion disappears when you average everything together. Ray explains that when exposures are too long, like the 270-second exposures used in the Hubble images, all that movement gets lost. The jets blend into the coma. The rotation disappears. Everything turns into one bright, smooth blob. That's why Ray says he can't see any spinning or swirling in the Hubble data, even when he tries to run time-lapse sequences. The data is simply too overexposed to show motion. In contrast, his backyard images tell a different story. In his time-lapse videos, the jets clearly move backward and appear to swirl, almost like they're being carried by a flowing current. Ray even mentions that viewers have asked him to slow these videos down or add timestamps because the motion is real and visible. That kind of feedback doesn't happen when nothing is there. Another important point Ray makes is that these features don't depend on one specific processing style. He can process the images in different ways, adjust contrast, change brightness levels, and the same structures still appear. The cone-shaped front doesn't vanish. The elongated tail doesn't suddenly disappear. The jet-like features keep showing up in the same general region. Ray then takes this a step further and directly compares his backyard images with two other things. First, he compares them with the raw Hubble data that he processed himself. Second, he compares them with the final image released to the public. And what he finds is striking. His backyard images line up much more closely with the raw Hubble data than with the released image. In his comparisons, Ray points out that his images show more coma, more tail, and more visible structure overall. Even with short exposures of 40 or 60 seconds, his images capture details that are missing from the released Hubble image. And remember, he's doing this from the ground, through Earth's atmosphere, dealing with light pollution and weather. He's not using a space telescope. Ray is also very careful to explain why he doesn't think these features are artifacts. Artifacts tend to show up randomly. They change position. They disappear when conditions change. They don't repeat in the same way over and over. But what Ray is seeing is stable. The structure appears across many nights. The jets appear in the same general orientation, and the motion follows a consistent pattern. If the goal is to understand how an object behaves, should we prefer images that look clean or images that preserve motion and detail? Ray's answer is clear. Detail matters, even when it looks messy. By comparing his own images, the processed Hubble raw data, and the released image side by side, Ray shows that the differences are not subtle. They're obvious once you know what to look for. The coma is larger, the tail is clearer, the jets are visible. And when you see that consistency across so many observations, it becomes very hard to dismiss it as coincidence. Ray's final point here is important. He says the released image does not show the full reality of what the data contains. Important structure is being lost due to exposure and processing choices. That doesn't mean the image is useless, but it does mean it's incomplete. And once you accept that idea, the conversation naturally shifts from this one object to something much bigger, which is how modern astronomy actually works and how it might need to change going forward. Because here's the thing we don't always talk about. Astronomy today is no longer just about building bigger telescopes. We already have incredibly powerful instruments in space and on the ground. What we do with the data they collect is just as important as the hardware itself. We're talking about decisions made after the photons are already captured, decisions about exposure time, cleanup, sharpening, and presentation. Those choices shape what scientists notice first and what the public believes is there. Let me ask you this. If two teams look at the same raw data and walk away with different visual stories, which one should science trust? The honest answer is not one or the other, but both, as long as the raw data stays open and the assumptions are clear. That's why Ray's work matters beyond 3i Atlas. He's showing that access to raw data allows independent checks, fresh eyes, and new questions that don't always come from inside big institutions. This is actually how science has moved forward many times before. In the past, strange signals were dismissed as noise until someone outside the main group took a closer look. In astronomy, reprocessing old data has led to new discoveries, from previously missed asteroids to faint structures in galaxies that were smoothed away in early images. The data didn't change. The questions did. And this is not anti-NASA or anti-institution. Large organizations have a different role. They need to communicate clearly, avoid confusion, and release images that make sense to millions of people at once. Clean images are easier to explain. Messy images raise questions. But questions are exactly where discovery starts. Do you think this object is natural or something else? Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.